American accent. Very good.
Okay. All right. I'm going to be talking briefly about Bessel functions, and I found a book that had a few good pieces of information in it, and so is it over in the library, Bessel Functions for Engineers. It's reasonably old, but the information's still good. Okay. Some interesting things about the Bessel, or about Bessel himself, or about the process, was that apparently a number of other mathematicians or scientists had been working on it prior to Bessel's involvement. Leonhard Euler had done some work that he apparently had come up with the differential equations with the same form that's considered the generalized Bessel equation. Then Lagrange later on, not too much longer, he was playing around with the infinite series with the same coefficients that are coupled with Bessel's name. And but then later on, in 1824, shows here, about there, that Bessel actually wrote his memoirs and published them in 1826, and that was close to 100 years after some of the other guys had actually been doing it. So he still gets all the credit apparently, but others had been before him. Okay, one of the things that he worked with was the, or as it says here, he found an astronomical quality or quantity termed the eccentric anomaly, theta, and can be, okay. And he came up with this infinite series that theta equals x plus a1 times sine of x plus a2 sine 2 of x, and so forth. It can be shown as the summation of a to n sine nx plus the x, and x being represented as theta minus x sine theta. Then the next process would be to find out what all the a coefficients can be calculated as. And so we begin a process where the first step he did with this series was to differentiate it. And once he differentiated, let me go to this page. Okay, so we have the original infinite series shown as a summation, and then he differentiated. And so we still have the infinite series, and then we reform it as being d theta times dx times the infinite series, and then just rewrite it as a summation. The next step was that he... Oh, okay. The next step that he did was to multiply both sides by cosine of nx. And then he integrated both sides, which made a very clever move. And by integrating both sides, then he could rearrange. Okay, now if we were to complete the integration of cosine nx dx, we get sine nx evaluated from 0 to 2 pi. And when we evaluate that from 0 to 2 pi, we get this value 0. Going back to continuing the integration of this term, we get a summation of a to the n times the quantity 1/2 cosine nx sine nx plus nx divided by 2, and then evaluated from 0 to 2 pi. Once we apply the limits, we find that the first portion of the terms inside the parentheses goes to 0, and we're left with n times 2 pi divided by 2, or just n pi. So n pi times an is simplified to the sum of n times pi times an, n going from 1 to infinity. Sorry about that. So now we can rearrange that equation so that it says an is equal to 1 over n pi times the integral from 0 to 2 pi of cosine nx d theta. Again, remembering that x is equal to theta minus x sine of theta. And going back to the book, that's where, same as this equation number 6. So that's a way to determine what all of the coefficients are for the series that he had, to where we had theta equals x plus a1 sine x plus a2 and so forth. All the values of a are calculated in this mode. Okay. Now, after we've substituted theta minus x sine theta for x in, let's see if I can put this up here again, previous page, where we had this form of an equals this quantity, we replace the x with the theta minus x sine theta, and it becomes this equation, an equals 1 over n pi times the integral from 0 to 2 pi of cosine times n theta minus z sine theta d theta, where we replace n of x with z. Okay, now we're going to substitute. Right here where it says an, we're going to replace that with 2n times jn of z. And we put that in. Just like this, where 2n jn of z is equal to this equation. So we're replacing an with this term. At that point, now we're going to move the 2n to the other side, and it becomes the j of n of z equals 1 over 2 pi times the integral. Okay, now and as I say, this function satisfies the differential equation of the second differential of y plus 1 over z times the first differential of y plus 1 minus n squared over z squared times y. If we multiply both sides, or multiply through by z squared, then it becomes this form. And this form seems to be the classic form everywhere I looked for Bessel form or formulas were in that mode. So at that point we've developed from starting from this infinite series at this point, reaching this condition right here. Okay, at this point the book attempts to show that it satisfies some cases. And it said the first simple case where n was equal to 0. And so we're going to replace Jmn of z is going to become J0. And the 2 pi moved over to the other side. Okay. And we're going to call that y. Now if we differentiate y right here, then it can be put in this form. So we still have the integral, but we're differentiating cosine times z sine theta d theta. And when we differentiate that with respect to z, then we get sine times z sine theta times sine theta d theta. Now at this point, okay. Have we reached this condition? Let's see, right here, where, let's see, no, it's already, excuse me, already differentiated, so we're in this position right here. Then what he did was he pulled out sine of theta d theta, or the minus sign that was in front, sine theta d theta, and rewrote it as d of cosine theta. Putting that back in here, the minus sign is gone when it went out with the sine theta. And d cosine theta is replaced in this position. Okay, cosine is now the variable. Cosine of theta is can be considered the variable, and sine of z sine theta would be the constant. So at that point, when we take the integral of it, we get sine z sine theta, which was constant, times the cosine of theta, evaluated from 0 to 2 pi, minus this term z from 0 to 2 pi times cosine z sine theta, cosine squared theta d theta. And when we evaluate this term from 0 to 2 pi, that goes to 0 because sine of theta was 0, and all multiplies together. And we're back to the first derivative of y with respect to z would be just this term. And going back to the book, that's right here, where first derivative of y with respect to z, this term went to 0. We're left with this term. We move the z over to the other side, divide both sides, and we have this term at this position. Okay. Now, unfortunately, that's about as far as I got of understanding how this developed and exactly how to use it. If anybody's gone any further than that, we can go into discussion mode. Questions?
Does anyone want to continue? Okay. You want to continue? Thank you. So we will continue what we started actually with the plates, and we will leave these Bessel equations to Mr. Andres, whom I thank for very nice presentation, as well as one of other students next time. But I just remember many years ago, many years ago, someone asked me why the Bessel function is called so. Okay, that was a question that was posed. An answer that I gave, I don't know whether it was a successful answer. I said that because someone else introduced it before him. No. That is why it is called Bessel function. Someone else introduced it before him. And interestingly, W.T. Koiter writes that there is this, approximately writes, there is this principle in science if a theory bears someone's name, this ought to mean that the first discoverer was someone else. I read this many years later. But we are not going into such philosophical matters today. Today we will continue our discussion about theory of plates and shells. So we said that if one dimension is much greater than the other two, then we talk about beam, bar, or column, depending on what this system is working. Say, beam means it is bending element. Bar, that is tension compression element. And column, that is both bending and tension compression. Okay. Now, if one dimension is much less, okay, in the first case, if one dimension is much greater than other two dimensions. Now is if one dimension is much less than other two dimensions. That is called thickness. Then we talk about the shell, if the middle surface is not straight. And we talk about plate, if middle surface is straight. Okay? And we are talking about theory of plates and shells now, as I said. Now, there is a book on this topic. That is a classical book. And this book is The Theory of Plates and Shells. And this book is written by Stephen, it's written here, but his name is Stepan. As this person is from Ukraine. His name is Timoshenko. Timoshenko and Voinovsky Krieger. Okay? So Timoshenko was a Russian scientist, but just immediately after the revolution, he thought that was too much for him, and he decided to leave. Went to Yugoslavia and then to United States. He passed away in Switzerland in 1972. Now, we will talk about the plates. So, as we said, we have several surfaces. Okay? And so there is this outer surface, there is inner surface, and there is this one that I call middle surface, capital omega. So omega 1 is upper surface, omega 2 is a lower surface, and omega is a mid surface. Now the distance between outer surface and inner surface, or two surfaces, is called h, and it is called thickness. H. Now the sides of this plate, say, for example, in this direction and that direction, this is called A and this is called B, denoted by A and B. So H is much smaller than A or B. Now, we have coordinate systems now. In omega, in the mid-surface, we are using coordinates x and y. Okay? Now there is a third dimension, z, that is perpendicular to xy, and that is a thickness direction. Z is orthogonal to omega. Now displacements, now what is displacements? If we take a point, any point, in the plate, so this point can be on the middle surface or it could be just inside the thickness, anywhere. This point undergoes some displacements, and displacements are u in x direction, v in y direction, and w in z direction. There are 3 displacements. This plate has 3 dimensions, u, v, and w. Now, u and v are called in-plane displacements, and w is called out-of-plane displacement. And or transverse displacement. Okay? So we said already that the equation itself, this equation that I will write down, actually, look, here is an equation. That is a differential equation for the plate. D, and then these triangles, which are delta, del, and I will write what this operator means. D, del, del, w, plus rho h, d2w, dt squared, that is for vibrations I wrote, equals qxyt. Now, if we want to write for bending, then it is d del del w equals q of x and y. Now what is del? That is a Laplace operator. And that is d2 dx squared plus d2 dy squared. Now we can write down it better. Del del equals what? That is d2 dx squared plus d2 dy squared. And of the same d2 dx squared plus d2 dy squared. Or that is just this operation squared, so to say. So that is d4 dx in fourth power plus 2 times d4 dx squared dy squared plus d4 dy in fourth power. So if I will just write it down, then D is a flexural rigidity. And equals E h cubed 12 1 minus nu square. Now E is modulus of elasticity. H, as we said, is thickness. And nu is Poisson ratio. which says actually that if I have a strip, for example, and I am causing to this strip to have, so that is a load. This load causes this strip to elongate. But, so as a result, so we will have L plus delta L. Okay? So that we will call it delta Lx. Okay, that is an elongation in x direction. So then there is a shortening in y direction. And so delta Lx divided by L is called epsilon x. That is deformation in x direction. And then epsilon in y directions then we have, because it shortens in y direction. So this is, it turns, Poisson says that epsilon y is proportional to epsilon x. You are using tensile load in x direction. In y direction, it undergoes shrinkage, so to say. And this coefficient, we could write down that this is alpha times epsilon x. But because epsilon x is positive, then epsilon y is negative, means that alpha must be negative. So therefore, he did not want, we don't want minuses, so to say. Therefore, alpha was denoted as minus nu, where nu is positive. So therefore, epsilon y equals minus nu epsilon x. Okay. So this is a material property. So E and nu are material properties. Okay? E and nu are material properties. Now we see one thing. Yeah, that is actually enough. So we already mentioned that. Okay, so these rules that we talked about Bessel equations, because Bessel's equation was done by someone else, but we don't know. I mean, Germain-Lagrange equation probably is called because Germain and Lagrange were first people. So sometimes it is called according to first people, sometimes it is not called according to the first people. Now, Germain and Lagrange wrote this equation, that is correct. They wrote, but de facto, they did not prove the equation, they just wrote something. And she, as I said, won a prize set by Emperor Napoleon, okay, for writing this equation. But proof of this equation comes much later. Proof was given by a German scientist, Kirchhoff, and later an Englishman, Love, L-O-V-E. So Love has a book which is called Mathematical Theory of Elasticity. And some people think, so this book is enough for elasticity, plates and shells, and more or less everything in mechanics. By the way, his name is, I think, written like this. So therefore, probably Beatles, now this English group, maybe that is what they meant when they said all you need is love. So probably they meant this book, otherwise they would have not composed the song. Okay. Now D is called bending stiffness or flexural rigidity. Now this, what they did is actually generalized Bernoulli-Euler theory of beams. So you may want to write down generalized. Almost every sentence that I say sounds very trivial, very simple, very understandable. But if you do not write all of them, then at some moment this quantity of not written material will go into quality of not understanding. So I'm recommending that you write it down. Now, there is this Bernoulli-Euler theory of beams. Now, paying attention when we say Bernoulli and Euler theory of beams. We should also say that beam does not know about Bernoulli and Euler. I mean, beams themselves never met Bernoulli or Euler, maybe. And therefore, these theories belong to Bernoulli-Euler. They are describing something of the beam. So some beams behave as Bernoulli and Euler predict, but there are some beams that they don't, so to say, recognize the Bernoulli and Euler. No, they behave differently. So under this, for example, there is, we have okay, so there is therefore other theories like Bress. Bress is a Frenchman, Timoshenko from Russia. Yes, there is Bress-Timoshenko theory of beams. Okay, so actually we have supermarket, I would say. Supermarket of theories. Okay, we have, say, in beams, we have Bernoulli-Euler, then we have Timoshenko, Bress, and we have many theories. Complexity increases. So, analogously with plates. So we have Germain-Lagrange equations. Then we have something like Mindlin plates. Then there are Reissner plates, etc., etc. There are many theories. So each theory catches something additional. Okay? The engineers very often are unaware of this, and they, I would say, often idolize a theory. Okay? Actually, they think that it is the theory because there is one. They know one thing, and therefore they, I mean, when something does not work, they are at loss because they cannot see that there could be another theory. Because why should be many theories for the same, some innocent beam, say this is a beam? Why there should be various theories for such a beam? Okay, it turns out that if beam is short, for example, this is also a beam, okay? Then, and this is a long beam. So this for long beam, we should use one theory. For the short beam, suddenly, this is more of the three-dimensional bodies, right, somehow. This is already close, because this length now, here is this length. This length is not very much more than other dimensions. Here, this length is much more than other dimensions. So then what we are seeing that when it shrinks to something smaller, I'm not going now to break this pencil because it is not mine, then you have to use three-dimensional theory. So at least one must be aware. Now, what was the motivation actually of Miss Germain? What she said is as follows. she said very simple things and claimed the prize. Look, please, she said. So this is a plate. Okay? This what I'm holding is a plate. Yeah, the sheet of paper is a plate. Now she said, in x direction, this is actually a beam. If I would cut a strip in x direction, then this is a beam. If I will cut a strip in y direction, this is also a beam, but a different beam. So, in x direction, she says, I should have something equation like EI d4w dx in force power equals q. That is a load. That is a force order differential equation for the beam that is in x direction. Now, in y direction, as we said, that is also a beam. Therefore, the same thing should be done. EI d4w dy force power equals q, she said. Therefore, says Miss Sophie Germain, she says, therefore the equation should be sum of this. Okay, this term. EI d4w dx force power plus d4w dy force power equals q of x. Very simple reasoning, very transparent, I would say, reasoning. But it was no one else did it before. Now Lagrange, as we said, very famous French mathematician, French engineer, was a chair of the committee. Okay, so as I said, Lagrange was a chairman. Sophie Germain was the only entry. That also shows, you see, there is a lot of money put there, and there is only one entry. That means that others did not have any idea how this equation looks like. Now for us it sounds like trivial. On the other hand, she was a genius. So Lagrange says as follows. This equation by Miss Germain is a very good equation, but it is not correct. It cannot be. This equation cannot be correct. Why? He said that I have this strip and that strip. But what happens if I have a strip in this direction? Some x1 direction. Then, he said, it is necessary that these operators should be independent of rotation. Here, only in x direction I have a strip, and in y direction. So therefore, I should have a strip independent of rotation. Therefore, he says, I'm adding additional term. That this term will take care, and he added one term. So if one wants to do arithmetics, so to say, there are 4 terms here, 1, 2, 3, and 4. So out of the 4 terms, 3 were given by Germain, and 1 term was given by Lagrange. So to say Lagrange, as if has 1/4 of the contribution, if we want to arithmetize, so to say, a contribution. But she won the prize because he was a chairman. He was not eligible for the prize. So, and no one knew how to prove this equation. I mean, is this correct? Or it makes sense, but no one knew, so to say, how to get this equation until Kirchhoff later. Okay, let us consider now also one can see as follows. If I have this strip that has just length is 1, then, and the height is h. Then moment of inertia is 1 times h cubed divided by 12. That is a central moment of inertia of the rectangular cross-section. So it was proved that actually this expression is not correct. EH cube over 12 is not correct. It should be EH cube over 12 divided by 1 minus nu square. And that is D. That is this flexural rigidity for the plate. That means that plate equations do not automatically reduce to the beam equations because there is this Poisson effect. Indeed, plate is something that has two directions, and these two directions are interacting. They are dancing together, so to say. Because they are dancing together, Poisson ratio should be there. Because Poisson ratio takes into account interaction of x-y directions. If you are pulling in x direction, then in y direction something happens, and there is Poisson effect. So plate equation does have this, and that is this comes as 1 minus nu square. But this effect is not very big, because if nu is 0.3, then 1 minus nu square, so nu square then is 0.9, 1 minus nu square is 0.91, so approximately 0.9, which gives just to the increase of flexural rigidity by about 10%. Nothing else. Let us first not obtain this equation, say, rigorously, but solve some problems. Imagine for 1 second that the load is given like this. Look, this load is actually also here, everywhere. That is a distributed load. That is a distributed load. And I just showed maxima. So to say, this qxy equals a sine pi x over a times sine pi y over b. Now what is this a? A is a side in x direction. Look, that is x direction. B is a side in y direction. So what we have is sinusoidally distributed loads. So this is how these loads look like. I mean, before that I just showed you this line and that line, but that is how these loads look. The question is how to find the displacement. So this is an equation. D for W dx in force power plus 2 times D for W dx squared dy squared plus D for W dy in force power equals A some constant that is given, sine pi x over A plus sine pi y over B. Now, pay an attention, of course, that W depends upon x and y. W depends upon x and y. And therefore, this is a partial differential equation. Therefore, the derivative signs are partial derivatives. So when we have a differentiation with respect to x, we write dw dx. When we have differentiation with respect to y, we write dw dy. Now, what are the boundary conditions? Boundary conditions are, imagine that they are, so to say, simply supported. What is simply supported? Like in the beam in this particular case, W equals d2W dx squared equals 0. That means the displacement equals 0 and the bending moment equals 0. Here in x direction. Here displacement equals 0, bending moment in y direction equals 0. So this is when x equals 0, x equals a. On both sides, they are simply supported. on both sides in x direction. They are also simply supported on both sides in y direction. So that means that they are simply supported all round from all 4 directions. Now, function that looks like this satisfies all these conditions. So that is capital W, sine pi x over a, sine pi y over b. So this is actually proportional to the loading itself. Here we have a, sine pi x over a, sine pi y over b. Here we write W. Okay? Because this function is 0 at x equals 0 and y equals 0, of course. Now it is also 0 at x equals a. At x equals a will be sine pi a over a, sine, or just sine pi. Sine pi naturally equals 0. Analogously, when y equals b, we get sine pi. Second derivative of this one at x with respect to x is its function itself times some constant. Second derivative of this one with respect to y with respect to is proportional to the function itself. Therefore, we can substitute this expression into, please write down here 1, equation 1. And we get this relationship. D. Now, fourth derivative with respect to x gives us pi over a in fourth power. Fourth derivative with respect to y gives us pi b in fourth power. Now, second derivative with respect to x gives us minus pi over a squared. Second derivative with respect to y gives us minus pi over b squared, but minus times minus gives us plus. Okay? So from here, w equals this a over d times pi over a squared plus pi over b squared. Or, now I substitute, yes? I found capital W, which is this, divided by this. Now I have to multiply by the function sine pi x over a, sine pi y over b. So that is W. You see, in this particular case, we solved the problem immediately. So let us calculate what happens in the middle, displacement in the middle point. I have to substitute x equals a over 2, y equals b over 2. Now, how much is sine in the middle? Sine pi x over a. I substitute instead of x, a over 2. So we get sine pi over a over 2. A and a are canceling. Sine pi over 2, which equals 1. So sine functions equal 1. So we get WA half B half equals A divided by D pi A squared plus pi B squared squared. So we solved the simplest problem for the plates. That is actually, there is no problem that is more simple than this. However, we immediately observe that q of x does not have to be such a nice function as I gave you. Q of x can be any type of function. For example, if this plate is a roof of some building, for example, and it snows, then one could anticipate that the function of the loading can be any function. So we can write down that it is q as a function of xy. So this is an arbitrary function of xy. Question is what we do for the arbitrary function of xy. So for this arbitrary function, we naturally represent the function w as a series. Actually, in this particular case, we could call it Fourier series. So Wxy equals some infinite series, m from 1 to infinity, n from 1 to infinity, w sub mn. So this is an index. Okay. M is index, n is index. So that is sine m pi x over a, sine n pi y over b. Now what is m? M. Let us look what m is. What is m? In sine m pi x over a. If m equals 1, so then it is pi x over a. This is this function. Such a function. Now if m equals 2, it is this guy. M equals 3. That is m equals 3. Now, what would you call an m? What is m? Mr. Panteras, can you suggest what m is? Say physical interpretation of m. Mr. Bereznoy.
Number of sinusoidal waves.
Okay, let us write down one of the first answer. Reply. M, what is this? Number of sinusoidal waves. Question, is this correct or not? There was an answer, number of sinusoidal waves. Mr. Gomez.
Is it correct?
I'm asking.
It is correct. Oh, well,
You are asking or you are returning the answer?
I'm asking if you're asking me.
I'm asking you whether the statement was correct or not. Mr. Plasencia? Say it again?
No, because a wave, if you keep having four, for example, you have four, that would be,
M equals 4, you say?
that's only two.
Yeah, only 2. Okay. M equals 4, 2 waves. Okay, so then what is an M? Number of half waves. Okay, we half sine waves. Number of half sine waves. Indeed, look please here. Here we have 2 halves. Here is 1 half. So M is number of sinusoidal half waves. It's correct. In x direction. Let us write down, in x direction. Now what is then n? Mr. Bereznoy. What is n? Mr. Plasencia?
Half waves on a wave.
Yeah, number of half waves in y direction. Okay, so m is number of half waves in x direction, n is number of half waves in y direction. Now let us represent Q in analogous form. Q. Do you remember we had this any function Q? Any function Q can also be represented as double series in terms of sine n pi x over a and sine n pi y over b. And here coefficient is Q sub mn. Now the loading, please write it down, Qxy we know. I can just measure point by point, so to say. For example, if it is a snow, then I can measure actually, just take a meter and stick in various places, and I know the height. Is it right? And then I will multiply by density, and I will calculate what Q is. So Q we know. Please write down, Q is known. If we know Q, how to find capital Q? If I know small q, how to find capital Q sub mn? That's a question. Why I want Q sub mn? Because it's easier for me to operate with Q sub mn instead of Q. This is like, can you bring any example from life situation where, we are interested with this contribution? Okay, for example, you could imagine also that is, fit students get this in, this copy of what I'm saying. But imagine that you are invited in a party for someone, but you say you cannot participate. You cannot go to the party. But you can send a contribution to the party. So you are not there, but there is a contribution. So actually, what we are interested here is there are various contributions here. Q sub mn is a contribution sent by m half waves in x direction and n half waves in y direction, for that party. For example, we want to buy a gift because there is some beautiful event happened at work or somewhere. So these are actually contributions coming from various sources. Okay, in this particular case, happily we have infinite sources. It goes from 1 to infinity and goes from 1 to infinity. Generally, in life situations, this does not happen, of course, unfortunately. People do not get infinite gifts for such an occasion, for example, good occasion. So these are contributions we may want to write. At least this word contribution is a correct word. Maybe explanation is too down to earth, but still it's not incorrect. So what we do is as follows. Now, m and n, we know what is m and n. M and n are numbers that are running from 1 to infinity. So we can actually call them def, D-E-A-F, def summation numbers. Def. Why we call them def? Because they don't hear, so to say. You see, they are not specific number. They are, I have to take first 1 and then 2 and then 3, so they are running everywhere from 1 to infinity. So this is a summation number, because it's not important. If I would have written here P and Q, then I would write P and Q, and it goes from 1 to infinity, 1 to infinity. It's not important how I call it. So it does not hear the name, so to say. So def index numbers we could call. We don't have to call them, okay? I'm calling it just because for us to digest this food better. Now we take some other numbers, j and k. Now j and k are not def. They are specific. J and k are not def. They are specific numbers. Now what is specific numbers? Mr. Andres, what would be specific numbers? For example, j equals how much? How many? J. Mr. Panteras, how much is J? Okay, give me a number. 2. J equals 2, for example. And K? 1. Okay, so we can choose actually specifically J equals 2, K equals 1. So these are specific numbers. Sometimes questions are very simple and demand only simple answer. So J and K are fixed. Okay, so we just remember for ourselves how much J and K are. Now what I'm saying is as follows. Let us multiply left-hand side here in this equation. So I called this equation star, and this equation I called double star. Our equations are starring in our movies. Okay? Now I will multiply then in double star by sine j pi x over a, sine k pi y over b. And then integrate dx dy. That is what I'm going to do. Now remember that j and k are specified. It depends on your will, on your wish, on your will, on your decision. Now, we have m from 1 to infinity, n from 1 to infinity, q sub mn. And what is left now here is sine m pi x over a, sine n pi y over b. That was there. Now I multiply it by sine j pi x over a, sine k pi y over b, dx dy. Now this double integral can be represented as a product of two single integrals. As a product of two single integrals. That is, integral from 0 to a, sine pi x over a, sine j pi x over a dx, and that equals, and then sine n pi y over b, sine k pi y over b dy. You wrote this? Now we will look at these integrals. Let us take the first one. We call it result is sine m pi x over a, sine j pi x over a. So this we call b, capital B, mj. Why it is mj? Because it depends upon m, it depends upon j. Now, j is fixed, m is running. M is 1, 2, 3. M can be an m is 1, 2, 3. First I have to calculate m is 1, m is 2, 3, 4, etc. And here j is fixed. Now these functions can be easily checked as they are so-called orthogonal functions. Means that sine m pi x over a, sine j pi y, j pi x over a, integral from 0 to a, equals 0 if m does not equal j, and equals a over 2 if m equals j. So write down for the next time. Homework number 1 is verify this. Verify this, that this equation is correct. Now, if this is the case, then this guy is what? Please write down here. This is B, the same thing, BNK. BNK. And you can write down, I'm not going to write, it equals 0 if n does not equal k, and equals b over 2 if n equals k. Please verify that homework number 2. Verify means do this integration and check that that is correct. So then what we are getting is as follows. Look, please. Double integral qxy sine j pi x over a sine k pi y over b dx dy. So that is what we did here. We multiplied left-hand side by this. J and k are specific. We know what that is. For example, Mr. Penteras chose j equals 2, k equals 1. And each of us can choose his number. Now, this is double summation. M from 1 to infinity, n from 1 to infinity, bmj, bnk, qmn. And that is a summation. M and k are def. They take values 1, 2, 3, 4, 5, 6, 7. I'm stopping here because otherwise it will take infinite time to number all of them. And
we'll be running out of recording time soon.
Fine. And then we have, look please, j is specified. bmj is always 0 when m does not equal j. So only when m will hit j value, we will get a over 2. Otherwise, there is 0 contributions. Now here is b and k. N also is running when n equals k, this equals b over 2. Now that means that m should be equal j, and n should equal k. Otherwise, that is gone. That is 0 contribution. So we are getting this expression. I will continue next time. Now, next time I would like to have as follows, as a presentation. Mr. Andres will continue presentation about Bessel functions for approximately 20 minutes. And Mr. Bereznoy will continue the rest of the time, and I would like that you both talk to me so that we will know what you are presenting. We would like that there should be a coherence in the presentations. Thank you so much.